So good afternoon, everyone, and welcome to the Communication and Signal Processing seminar. This is the second of this semester. There are two more after this. First, let me start by thanking Kate Goodwin and Shelley Feldkamp for doing all the hard work behind the scenes, and also the research areas for supporting this. So I'm delighted to introduce Amin Karbasi, who is a speaker today. He's currently I've known Amin for a while because his work initially was in sort of information theory and coding. That's where at conferences and stuff I've met him, including a Sigmetrics workshop. Anyway, so Amin is currently an associate professor of electrical engineering, computer science, and statistics and data science at Yale University. He's also a research scientist at Google, New York. He's been the recipient of several awards: the Bell Labs Prize, National NSF Career Award, ONR Young Investigator Award, AFOSR Young Investigator Award, DARPA Young Faculty Award, the NAE Granger Award, Amazon Research Award, Google Faculty Research Award, an award from Microsoft Research, Azure Research, Simon's Research Fellowship, and the ETH Research Fellowship. His work on machine learning, statistics, and computational neurosciences received awards at several premier conferences and journals, including Medical Image Computing and Computer Assisted Interventions Conference, AI Stats, Facebook Main Award from the AI Neuroscience Symposium, IEEE Communication Society Data Storage Conference, ICASP, ACM Sigmetrics, ISIT. His PhD work received the Patrick Binance Memorial Prize for the best doctoral thesis from the School of Computer and Communication Sciences in EPFL. With that, I give the floor to Amin. It's all yours.
Yeah, thank you very much for the very kind introduction. It is, I'm extremely delighted to give a talk at Michigan. It is really unfortunate that I couldn't be there, in person. And we were discussing with Vijay, when we can have the talk, and I was just trying to defer it to the time that we might actually be able to visit. Unfortunately, it doesn't seem to be possible anytime soon. So today I'm going to talk about sequential decision-making problem, and try to understand how much interaction a policy needs to have with the environment. Okay, so Bayesian decision making comes in many different flavors, and it's a central technique in numerous applications, from active learning and robotics to recommender systems and experimental design. And in all these problems, we'd like to find a good policy, ideally an optimal policy. And that maximizes some sort of utility, right? So do you guys actually see the slides?
Yes, yeah, we can see them, yeah.
Okay, good. Right, so I need, we would like to find a good policy, or maybe, ideally an optimal policy, and we also would like to, to know how much interaction with the environment we need. Such an ideal policy might need. So, so to start and to say, what kind of problems I'm going to talk, let me, let's consider a simplified troubleshooting example where, speaker like me tries to join a Zoom meeting by phone or by computer, or, you can think of your grandparents, right? And there is usually an issue, right? So, an agent has to, usually we have to find the, what is the root cause of the problem. And to do so, she can perform some simple tests, such as checking whether the phone is working, whether the phone sends, if so, whether it sends messages, and then, does the Wi-Fi work? or there is either a bug or not, right? So the result of each test will change the belief about what might be the root cause. And in this example, right, we have to reduce the uncertainty about the problem to a certain level so that we can act on a solution. Okay. So let's set up the notation based on our example. Here we have a set of hypotheses theta about the root cause of the problem, each with a corresponding probability, P of theta. We also have access to a set of tests, V. And any test, say I, has a random outcome, O, where the probability of the outcome depends on the root cause, which is formalized by the conditional probability. And we also assume that the cost of performing a test I is basically Ci. So in order to decide which test we need to perform, we have to run a policy. And what is a policy? It is a mapping from observations to tests. Okay, it's a decision tree basically. And depending, on which state the word is, and in our example, what is the root cause of the problem, the policy explores different parts of the decision tree. And finally, the performance of the policy is usually measured by a utility function that depends on the test that we selected and the outcomes of those tests. So the expected utility of a policy that I'm going to denote by F average is shown here, where the expectation is taken with respect to the probability of each hypothesis, or where, the probability of where the world is. Similarly, we can define the average cost of a policy. And here, S is basically denotes the set of items a policy select that depends on which state the word is, namely the root cause, right? So then there are two natural ways to define an optimal policy. In stochastic utility maximization framework, the problem is to find a policy that adaptively selects a set of K items. In our example, the test that maximizes the utility. Alternatively, in a stochastic mean cost coverage, we can define a quota Q of utility that we would like to obtain with the cheapest policy. So unfortunately, both problems are hard to approximate under standard complexity theoretic assumptions. So in the remaining of the talk, we will consider a structural assumption about the utility function that ensures tractability. So to do so, let me define a few important quantities. First, let's assume that we have observed a set of tests outcomes, X sub A here. So now we can define the conditional expected benefit of performing a new test S, a new test, as follows, where where we condition on the observations seen so far. Okay. And we're going to say that the function f from test outcomes to non-negative real numbers is adaptive submodular if the expected marginal benefit of any test does not increase as more tests are selected and their states are observed. So as we perform more tests, the expected benefit of a new test is going to decrease. So when the context is increasing, the benefit that we get from a test is going to decrease. So this is what we call the adaptive submodularity. So some of you actually may know, the classical notion of submodularity. Let me say, let's revisit the classical notion of submodularity and see what is the difference between submodularity and adaptive submodularity. So a function f, which is a set function now, okay, a set function f is called submodular if adding an element s to a smaller set A increases F by at least as much as adding S to the superset B. So here, just note that in the definition of submodularity, we assume that there is no stochasticity and all the outcomes are completely deterministic, and therefore there is no benefit in adaptive selection. Adaptive submodularity strictly generalizes the notion of submodularity to interactive settings by conditioning on observations and asking and here taking expectation with respect to the test we have considered so far. Okay. So the classical greedy algorithm, so submodular maximization, has also a natural generalization to the adaptive setting. So for the so how does a greedy policy works here? At each iteration, it myopically increases the expected objective value given the current set of observations, right? So we would like to pick k tests. At each iteration, we look, which test in expectation is going to give the maximum utility, given condition on the set of observations we have had so far. And for the stochastic utility maximization, the seminal work by Golovin and Krause showed that the greedy policy achieves the tight 1 - 1 array approximation to the expected reward of the best policy. That is, that takes exponential time to compute, right? So this simple greedy policy not only achieves a constant factor approximation, it is the best approximation for any polynomial time policy. As long as the function is adaptive submodular that I have defined and is adaptive monotone, meaning that if I select a test in expectation, the gain is going to increase. So no test is going to hurt the utility. We have generalized the result for the case that the function is simply adaptive submodular, so the test might actually decrease the value. And we came up with a randomized greedy policy that also achieves a constant factor approximation to the optimum. So how about the alternative view where we have a Kotak queue? So there is, we can also define, we can also have a greedy policy for the stochastic mean cost coverage problem. But the only thing is that we have to make two simple modifications. First, we are going to change the the stopping criteria. Before we had to, we wanted to select k tests. Now we are going to continue selecting until we reach Kotak Q. So that's the first one. Second, in order to select a test or an item, we consider the expected marginal benefit divided by the cost. So we look at the expected reward per unit cost, okay, and select the test that maximizes that. Good. Golovin and Krause in their seminal work conjecture that as long as F is adaptive monotone, adaptive submodular, the greedy policy that I just explained achieves a logarithmic factor approximation to the best policy. And there has been a couple of works that try to basically prove this result under much stronger conditions about the probability distribution or the function, but the general conjecture has been widely open since then. And in our recent work, we showed that basically the conjecture is true. So we showed that as long as F is adaptive monotone and adaptive submodular, then the greedy policy is indeed going to achieve a logarithmic factor approximation. Okay, so let me briefly explain what has been the bottleneck and what was why did people couldn't actually solve this problem for a long time. And here is the main challenge. So let's consider again the simple situation where we have a submodular function. Okay, so It's not adaptive submodular, it's a simple submodular function. Given a submodular function f, if we threshold it by constant alpha, the resulting function g will still be submodular. And this property automatically provides a reduction from submodular maximization to submodular coverage. So basically, if this reduction holds, which holds for a submodular function, then the logarithmic factor approximation is nothing but the result on the constraint submodular maximization, for which we know how to get it. So that result has been known for many years. Why this approach didn't work for adaptive submodular function? So here's the issue. It turns out that this property does not hold for adaptive submodular function, despite being stated in several papers. And there is this, we have simple examples to show that. So if you take a threshold alpha, if the function is adaptive submodular, you threshold it by alpha, it's no longer, it may not be adaptive submodular any longer. So we had to develop a new theoretical guarantees for the adaptive greedy policy. Okay. So how do we do that? In just one slide, let me tell you what is the proof technique related to the greedy policy, related to proving such a result, and it is by relating the greedy policy to the optimum policy as follows. Okay. So remember, pi represented a policy, right? And we are going to say pi tau is going to be the policy that runs greedy and stops when the expected marginal gain of any remaining element is less than tau. Okay, so with different values of tau, this policy is going to stop at different times, right? It's going to stop whenever the policy knows that the expected marginal gain of any other element is going to be less than tau. Okay. Now, what is tau sub L? It is the threshold such that the expected number of elements selected by the policy pi tau L is exactly L. Okay, and what we do is basically relate the utility obtained by pi tau L to the optimum utility by the optimum policy pi star. So basically we show that, as a function of L, how these two things are going to be related. And what this equation says is that as L increases, you are going to get more and more fraction of the optimum solution. And that is how to get the logarithmic factor approximation. Okay. So how, you may say, how this is related to, machine learning and all kinds of things. Okay, it's cool to show a logarithmic factor approximation. If you're not impressed by the result, let me.
Mr. Binger was talking about pinching the screen. iPads, which are made by Apple, have artificial intelligence in them that allow things to be viewed through 3 dimensions and logarithms. Logarithms, I don't understand it all either. And it uses artificial intelligence or their logarithms to create what they believe is happening.
Okay. Yeah. So logarithms are very important for artificial intelligence. Okay, so I think it's a good time if there are any questions. If not, I'm going to then talk about how
the question, just quick one. I mean,
sure.
So the adaptive submodular, what sort of are there examples of functions that are easily explained that are
All right. So for instance, let me just maybe about the generalized binary search.
Mm-hmm.
Okay, or 20 questions, right? So what is happening is that, in the generalized binary search you have, or in any active learning problem, basically, you have a set of hypotheses, right? And then whenever you perform a test, some of the hypotheses, let's assume the realizability case. When you perform a test, a set of hypotheses are not going to be consistent with the result, okay?
Mhm.
And so if you look at the space or the probability mass of the set of hypotheses that are not consistent, this is an adaptive submodular function.
Okay.
That is how people actually, you can basically, our result actually shows that for many active learning problems, it is possible to get log n, logarithmic factor approximation. Okay, so this is how it is done. Yeah.
So can I ask a quick question? So
Sure.
for example, in the binary question example you gave, what if there's a different cost for each of these queries? Is it still valid? And if I have a cost budget rather than having a budget on my number of queries, is it still valid?
So you're very good. So you're asking what happens if I have a knapsack constraint,
Mhm.
correct?
Yeah.
Yeah.
Instead of a cardinality constraint. Then I did not talk about how you can actually get those results, but and what is the algorithm? So the greedy is not going, of course, is not going to work, okay? Because it doesn't take into account the cost, okay? Or the greedy policy is not going to work. But you can run two policies, one that is greedily is going to select, the other one that is going to select per unit cost, and then take the one that gives you the maximum utility, that is going to give you a constant factor approximation.
Cool, thanks.
Good, very good question. Okay, so so note that a priori selections where we determine all the tests ahead of time before any observations, right? And fully adaptive procedures where we exploit the information obtained from the past selection in order to make a new selection are simply two ends of the spectrum. So in the remaining of the talk, I'm going to talk about semi-adaptive policies that can enjoy hopefully the guarantees of a fully adaptive procedure while carrying out fewer adaptive routes. Okay, so let's actually talk about active learning and what people call batch active learning as a simple example. Okay, so in batch active learning problems where the label of a subset of data points are requested simultaneously, right? We want to dogs versus cats, okay? So there are requested simultaneously, and in such problems, we would like to know which items to select in a batch, how to choose the duration of a batch, and of course, whether we can obtain any guarantees with respect to the performance of the, best fully sequential active learning policy, right? So, and the reason that people are very interested in batch active learning problems is that they have many agents and they can distribute, all these images to different agents simultaneously, get their, labels all at the same time. The question is, how can you do that? And whether you are going to lose anything, right, if you do it. With respect to a fully sequential policy where, one by one, you're going to do that. Okay. So now let me try to actually answer this question in the context of adaptive submodularity. So in particular, what we're going to do is we're going to define a semi-adaptive value of items. So a semi-adaptive value of an item E is going to be our estimate of the expected value of selecting this based on the information of the last batch query that we carried out and the set of items that we are selecting We are deciding to select, but not yet queried. Okay, so it is a generalization of the expected marginal benefit, right? And we're, the IS element selected by the semi-adaptive policy is the one that maximizes the semi-adaptive value, right? So which item are you going to select next in the batch? Well, it's the one that maximizes the semi-adaptive value. Okay. So this is how we are going to select items within the batch. But now the question is, where do we stop, right? Selecting items. Of course, if I continue selecting this way, at some point, my estimate versus the true values of these items are going to diverge. So at some point, I don't have enough information. My estimations are very bad, so I have to stop. Where is that point? So to this end, we define what we call the information gain as our estimate of the accuracy of the maximum semi-adaptive value. So we use the information gap to balance, between the loss on the performance and the number of batches queried, the number of batch queries that we have made. So once this value is less than 1 minus epsilon for a predefined epsilon, we are going to stop, and then we are going to query all the items within the batch. Okay. So what is so this is a pseudocode of the semi-adaptive policy for adaptive submodular maximization. So within a batch, we make sure that the total number of selected items is less than k, and the information gain is still above 1 minus epsilon, and then we select items that maximize the semi-adaptive value one after another. So what can we prove? First, we can prove that in log n times log k adaptive rounds of observation, this semi-adaptive algorithm can achieve an almost tight 1 minus 1 over e minus epsilon approximation guarantee with respect to the optimum policy that carries out all the k actions in a fully sequential manner, right? So there is going to be an exponential reduction, right, in terms of the number of interactions that we have with the environment. Before, it was k. Now it's log n times log k. So on the flip side, we also show that it is impossible to achieve a constant factor approximation with all detail log n batch queries. Okay, so you need log n. This is the minimum that you need. And then on top of that, we also show that the approximation guarantee of any semi-adaptive policy that chooses batches of fixed size will degrade with the factor of r over log r squared. So one simple way of parallelizing is that you just pick r items within each batch, right? And what we are showing here is that this is not a good way of parallelizing because the utility is going to degrade. What really allows us to get this very tight 1 minus 1 over e approximation guarantee is that the batch sizes are dynamic, and it depends on how much on our estimate of how good the values within the batches are. Okay. For the alternative problem, the stochastic mean cost coverage, we basically get the same result. We show that you can get the same logarithmic approximation in polylogarithmic rounds through a simple information parallelization scheme. So basically, in a nutshell, our results shrink the adaptivity gap in adaptive submodularity by an exponential factor. Okay. So now I'm going to continue the discussion into a different setting, a little bit different. So that is also a good point if there are any questions, because then we are going to change gear. Okay. So for the next part, let me talk about vaccination, which seems to be a controversial idea these days. Actually, running medical trials was one of the main motivations of Thompson, who was a member of the Department of Pathology at Yale, and who did, who is one of the founders of the Bandit. So, let's assume that we have K vaccines, where the efficacy of vaccines are some numbers between 0 and 1. We don't know what these numbers are, right? And we would like to find out which one has the highest efficacy. And in order to do that, we have to run, right? We have to run trials. So in the non-interactive setting, which is, huge, of course, I'm doing a huge simplification, but, this is a first order approximation of what is done in medical domains, also known as randomized trial. We randomly assign a patient to a vaccine, and then we wait W days, and we see which of the patients developed immunity and which one didn't, right? And then we average out the results, and that is going to be our estimate of the efficacy of the vaccines. Okay. Good. So this is a very simple procedure. It is also very fast, no matter how many patients you have, because you run everything in parallel, you only have to wait W days, right? What is the problem? Well, the issue is that if you do this during the trial, very few people will get the top vaccine. 1/k fraction, basically, right? So how can we do better? Well, we can think about interactive settings where, the nurse is going to administer the vaccine to patients one by one. But for each one, we have to wait W days, right? And then check the efficacy of the previous injections in order to decide which vaccine to do next, right? Good. So now here, a nurse is going to face a dilemma, which is called, which many of you know, which is called the exploration-exploitation trade-off, which is, should she explore an option that looks inferior, or exploit by going with the option that looks best currently, right? So on the positive side, if the nurse can solve this dilemma, then hopefully many patients will get the top vaccine. But on the negative side, because this is a fully sequential mechanism, it takes a long time. And in our example, it's going to, it depends on the number of patients. If there are T patients, and for each patient we have to wait W hours or days, it's going to be T times W. Okay. And there are indeed many ways, right? Many effective policies that efficiently balance between the exploration and exploitation. Here, I'm going to show two examples: upper confidence bound and Thompson sampling. That are going to do the job. Let me and I'm going to explain briefly each one of them, and then see what we can do about it. Okay. So to set the notation, in the interactive setting, patients arrive one by one. The nurse chooses a vaccine, which is among K different types. So it is denoted by AT, the action that is taken at time T, and then we wait for W days to check the efficacy, and the efficacy is the reward in the Bandit setting, which is denoted by RT. And what we want to do is to maximize patient's outcome overall. Okay, so we want to maximize the reward. And it's in its most simplest setting, the stochastic multi-arm bandit, we have find a number of arms, and each arm is associated with an unknown probability distribution P sub A. that is supported between 0 and 1. So the player selects an action at round T, and the environment reveals a reward RA sampled independently from P of A. And so, the goal is to maximize the cumulative reward, or equivalently, to minimize regret, which is the difference between the best fixed action in hindsight and the cumulative reward of the player over T rounds. And what the upper confidence bound algorithm does is an optimistic policy that uses the data so far to assign to each arm a value that is an overestimate of an unknown mean value. So here T sub I, indicates the number of times the arm I has been played by time T, and mu hat is the empirical mean. Okay. So in the beginning, the upper confidence bound of all arms are set to infinity, and then we play the arms. And once once you play the arms, the values are going to be updated as the sum of the empirical mean and the confidence interval. And the confidence interval is nothing but the standard concentration bounds that you get from like Chernoff. And UCB at each round selects the arm with the highest upper confidence bound in order to efficiently balances between the exploration and the exploitation steps. It's a very simple algorithm. Now, given a gap between the mean reward of the best arm and the remaining arms, so one can show that the UCB achieves the tight problem dependent regret bound that is only logarithmic in the horizon T. So pictorially, here's a picture. We have a non-sequential policy when the regret grows linearly with T, but the waiting time is only W. In contrast, if you use UCB, the regret only grows logarithmically with T, but the wait time is going to be linear in T. It's going to be T times W. What we're going to do next is, can we, achieve almost the best of both worlds? So basically, we would like to play, a number of arms simultaneously or in parallel, so that we only wait W days to see the result of each, of each batch. Okay. So now we have a more sophisticated dilemma. So as we, only receive information after all arms in each batch are played. So the way that we are going to parallelize UCB is as follows. We are going to gradually eliminate suboptimal arms while increasing the batch sizes. So how do we do that? Specifically, the player selects an arm A in the jth batch Q to the J times. Okay, Q is a number, which we set it to be T to the 1 over B. And then within the JS batch, an active arm is going to be selected Q to the J times. Then we are going to update the empirical estimate of the mean value and removes any arm that is suboptimal. What does that mean? Well, it means that the empirical mean of the arm is significantly below the current best arm. Okay. So this is the strategy that we are going to do. And so what is going to happen is that if we set delta as follows, okay, 1 over KTB, then the regret of the batch arm elimination will be bounded by T to the 1 over B times log T times the sum. So if we let the number of batches be on the order of log T, right? So if we set B to be on the order of log T, the regret of this batch arm elimination matches, what was for UCP. Okay. So basically, increasing the number of batches from log t to t only decreases regret by constant multiplicative factor. What is even more interesting is that this result is not only tight in terms of the regret, but also almost tight in terms of the number of batches. Basically, there is this very nice paper by Gao et al. Neritz that they showed that in order to obtain the optimal problem-dependent regret, any batch algorithm has to have at least log t divided by log t batches. And among friends, log t is a constant. Okay. Okay, so this is basically the picture now for the semi sequential policy. We achieve the same log t regret, but then the wait time only increases by a factor log t, and it's going to be exponentially better than the waiting time of a fully sequential algorithm. Good. So let me actually skip how we can do the same thing for the contextual bandit, right? So in the contextual bandit problem, the patients actually arrive with the medical history. And so we have to take into account what is the context. And in the simplest case where we have a linear contextual bandit, then we can basically show the same result that if we set the batches to log t, then we have a generalized linear contextual bandit algorithm that is run in batches, and it achieves the the sequential regret bound, the best sequential regret bound that we know of.
I mean, there was a question in the
Sure.
chat asking if you don't lose anything in the order, but do you lose anything in the constant in the bound?
Yeah, as I said, right? So there is going to be exactly the order doesn't change, but there is going to be constant is changing, right? That's correct. We lose in terms of the constants.
I had sort of a different question. It's more like if you want to explore a different aspect of it. Here, all the experiments are taking the same amount of time.
Yes.
They were different times. And you don't know the accuracy. What happens?
Right. So correct. So that's a good point. Here there is this line of work on delayed bandit, which can be combined, I guess, with this batch, but we haven't explored that direction.
Okay.
Yeah, but that's a very valid question. Application-wise, I think it is extremely important to, you want to be robust, right, in all these type of decisions, right? What we are showing is that you are really robust in terms of the number of interactions. The amount of information that you need can be obtained in log t interactions with the environment. Okay, the rest is constant, right? You also want to be robust against delays, and here we are not taking this into account, which I think it's an important aspect. Okay, now in the remaining of the time, let me because I promise I'm going to talk about Thompson sampling, which is an extremely nice idea. This actually Thompson, right, in 1936 came up with this algorithm. It works extremely well in practice, and for many years people didn't know why. There was no analysis. So how does that work? So in different literature, it is called different things. It is sometimes called posterior sampling or probability matching, and the idea is very simple. So what we are going to do is that we are going to keep belief about the parameters of the arms. We are not going to keep just numbers. Here we are going to have a belief, a probability distribution associated with each arm. And once, and in each round, it selects an arm with the posterior probability of being the best. Okay, so because there's probability distribution associated with each arm, then there's also a probability that every single arm might be the best arm, right? And so each arm is going to be selected with with that probability. And this is this randomization step is the way that Thompson sampling explores the environment. So as we select an arm more and more, its posterior distribution concentrates better around the its mean, and the player becomes more confident. So in practice, we don't have to actually find these probabilities, right, with respect to which we are going to select an arm. So in a very simple way to realize Thompson sampling is as follows. Let's say that D sub A indicates the distribution associated with arm A at time t, and then at each round we just sample independently according to D, and then select the arm with the largest theta. Okay, this is equivalent to what I said in the previous slide. And then once we observe the reward of the arm, we use the Bayes rule to update the distribution. Very simple. So now let me explain how we're going to parallelize. And again, let's consider the JF batch. So within this batch, and at round T, we sample arm independently according to D sub A and select the arm with the largest value, right? So within the batch, we do exactly as we did before. However, because we are not immediately observing the reward, we are not going to update the distribution. We just continue sample. How far we go? Well, we continue selecting elements until the number of times an arm is selected reaches a threshold. So each arm, as you can see in green, is associated with the threshold. So we keep sampling until one of them reaches its threshold. Then we are going to query all those arms and update the posterior distribution of all the arms selected in the batch. And then what do we do with the threshold that triggered the end of a batch? Well, we are going to double it. Okay, so and this is how it goes. I'm not sure that I see that it's frozen on my end, but do you see that?
Yeah, we can see this.
Okay, very good. Yeah, this is the problem with having two monitors. Sometimes it frozen. And okay. So the only thing that I have to tell you is how we update the beliefs. Okay, so because we are using the posterior distribution, we should choose a probability distribution in a way that it is easy, right, to compute the posterior, right? Posterior distribution is tricky. But for some probability distribution that is easy to do, and one of them is the beta distribution. So we initialize all arms with beta 1 and 1, which is a uniform. And then the good thing about the beta distribution is that the posterior is going to be within the same family, and it is easy to find. So that's it. So what do we get? Well, we can prove what we can prove is a similar result, where we show that it is possible to achieve the log T problem dependent regret with basically log T rounds of interaction, also for Thompson sample. Okay. And again, let me not go into detail how we are going to do that for contextual bandit, for the linear contextual bandit. So for here we also show the same result, but you can see there is the only difference with the previous one is that with lean UCB and those kind of things, is that here the regret, unfortunately, has d to the d to the 3/2, right? So it is suboptimal in terms of the dimension. And it seems that Thompson sampling really suffers from that. And there is a recent paper that shows that the classical Thompson sampling really has this problem. And there is an example that shows this suboptimality. Okay. Here so far I talked about multi-arm bandit and then linear contextual bandit. You can say, well, how about the case where the interaction is not linear, but it might be sublinear. It might be non-linear. And in that case, you may want to actually use a neural net that learns how the context and the rewards are related to one another. And so basically we extended all these results to non-linear bandit settings and show that you basically get the same regret bounds in the batch mode. Okay, very good. So, so today I just tried to present a few results about how many interactions we might need in order to achieve a goal. And for interactive decision-making problems, we saw that we can have we can decrease the number of interactions exponentially. For the bandit problems, we can do the same thing. We're going to have a submission, hopefully, to ICML that we show that for reinforcement learning, you can do the same thing. So you don't have to be fully sequential or see the rewards. And now, what is the take-home message? Well, you can, think of any learning problem that you have in mind, and many of them are actually, the solutions or algorithms are going to be sequential. Okay, and then you can go and think tonight whether it has, to be the case. Is it possible actually to parallelize it and have the number of interactions much lower than what a sequential algorithm is? And if you think that is the case, then please send me an email. I'll be more than happy to hear about it. Okay, thank you very much.
Well, let's thank Amin. Before I open up for questions, he has to leave by 5. So let's.
Yeah, unfortunately, if I don't, we have our son is in daycare and he's going to be placed by the curb. So.
So I had a question about the last comment that you mentioned about in the reinforcement learning context, parallelizing. Is it your setup that you have a generative model, or is it looking at it as like the Q learning thing? You have a data set, so you can basically explore. And, what is
so the offline and so right. So so it is. So we have the results for first for both. Right. So maybe I should not, once we have the results completely written, then I can claim something. So we have the results for both model free, okay, and model based under a general function approximation.
Okay.
That is to be very, very precise.
All right. So any other questions from people or in general? Give a few minutes for people to think about it.
Yes. I can also stop sharing, but I don't know, maybe it is.
Oh, that's fine. I mean, we can see you. But so in some sense, when you're parallelizing, in a way, you seem to have independent instances of the same thing, right? So, but if that somehow is a underlying setup.
Right, for the Bandit, because we don't have any states.
Yeah, so it's not a problem. I was talking more in terms of the reinforcement learning. You could have
Right, but with reinforcement learning, you need to know way more. Exactly, right. So it is not very, it's not easy to extend it. I agree. Yeah, it's pretty involved.
I can imagine that.
Yeah.
Yes, I don't see any more questions. So let's thank Amin once again.
Yeah, thank you very much for for the invitation. I wish that one of these days we can actually see each other in person.
That's true. Fingers crossed sometime.
Yeah. Okay.
Right, thanks, and have a good for the week. Yeah.
You too. Take care. Bye.
All right.